Hello, today we're going to look at L'Hopital's rule. This is actually in the integration section, however it's not exactly a technique of integration. We're going to use it to find limits, as we'll see. So we'll start by taking an example. What is this limit? What is the limit as x approaches 0 of sine x over x? Okay, so the first thing to notice is we can't just plug in 0. Okay, sine of 0 is 0 and x obviously is 0, so we get 0 over 0, so we can't plug in. But what is the limit? Well, you can try plugging numbers into a calculator. I had a little go at drawing this. Okay, and this is what this looks like, close to 0. Now we'll notice it's undefined at 0, maybe we could have a little circle in there. But it is fairly clear that as we approach, or as x approaches 0 from both the left and the right, that the y value, the limit of the function, is approaching 1. That looks pretty clear graphically. And what L'Hopital's rule is going to do is help us evaluate that algebraically. Okay, so we're going to apply L'Hopital's rule to various of what these are called indeterminate forms. Okay, so the first one we just saw, 0 over 0. Okay, and it's not really that we're plugging in 0 over 0 with some kind of limit that's approaching these values. Okay, so as we've seen, 0 over 0 we're not quite sure what to do with, and similarly infinity over infinity. And in fact, as we go through these rules, that's like 0 times infinity, we'll see in each case there's kind of two rules that we want to apply, and we can't apply them both. For example, 0 times infinity, well, 0 times anything is 0. Infinity times anything should be infinite, and we obviously can't apply both of those rules, so we're going to have to do something else. There's a few more examples. Infinity minus infinity. 0 to the power of 0, is that 0? Is it 1? Is it something else? 1 to the power of infinity, and again this is as we approach 1. Okay, is it going to get very big or very small, or is it actually just going to approach 1 or some other finite value? And infinity to the power 0. Okay, so there are all our indeterminate forms, and we're going to apply L'Hopital's rule to each of those. Okay, so let's take the first part of the rule, and this will apply to the example we've seen previously. So if we have this ratio, f of x over g of x, and as we approach some value c, they're both approaching 0. And we're going to assume that they're both differentiable functions. Then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. Okay, so we take the derivative of the numerator, the derivative of the denominator, each as separate functions, and we take that new limit. And just a quick remark here, this isn't the quotient rule. Okay, hopefully in differentiation you recall the quotient rule. You may have even applied this as the quotient rule by mistake on occasions, but this isn't the quotient rule. This is something different. We treat the numerator and the denominator as separate fractions and differentiate each one and then take the limit. Okay, and so the example we saw previously seemed like a prime example of where we could use this. Okay, they're both approaching 0. So we can use L'Hopital's rule, take the derivative of the sine, which gives us cosine, the derivative of the x, which gives us 1. You'll just notice here the LHR we have above the equal sign. It's not essential that you have that there. It's not wrong to not have it there. They certainly are equal. That's just a little reminder that we applied L'Hopital's rule here. Okay, without the LHR, it might not quite be clear what we did to get from this stage to this stage. So we put L'Hopital's rule, LHR above the equal sign. Okay, once we've done that, this is very easy. As x approaches 0, we get cosine of 0 over 1, which is 1 over 1, which is 1. And that's, of course, what we expected from our graph previously, but now we've shown that that's true. Okay, let's take one more example. Let's take the limit as x approaches 2 of x squared minus 4 over x squared minus 3x plus 2. And so if we try plugging in 2, we get 4 minus 4 in the numerator, which is 0. We'll get, 4 minus 6 plus 2, which is also 0 in the denominator. So again, we have this 0 over 0 form. You may recall from work on limits, we could actually factor the numerator and the denominator and cancel. But I think this is probably even quicker. Again, take the derivative of the top, derivative of the bottom. Take the limit as x approaches 2, which is now very easy. We can just plug that limit in. So we get 4 over 1, which is 4. Okay, so that is that limit. And if you had factored, you would have found the same thing there. Okay, so now we'll take the second part of the theorem, and it's pretty similar. Now instead of this going to 0 over 0, we're going to assume that the numerator and the denominator are each going to infinity, positive or negative, it doesn't matter either way. And if they're going to infinity, then it's still the case that if we take the derivative of the top and the bottom separately, then L'Hopital's rule gives us that these two things are equal. Okay, again, we're going to make this assumption that they're differentiable for this to work. And then if we look at part 2, this is slightly different. Now we're taking the limit as we approach infinity. And again, we're going to assume that it's 0 over 0 or infinity over infinity. So instead of a finite limit, now we have an infinite limit. But still the same rule applies. Differentiate f prime of x over g prime of x and still take the limit. And we've said that's infinity. It could also apply to negative infinity in just the same way. Okay, so we have our 3 parts. Let's take an example of this. Okay, so we have x going to infinity of e to the x over x squared. Clearly, the numerator, e to the x, is going to infinity as x goes to infinity, and x squared, it's the same. So we can apply L'Hopital's rule, and we get to here. Well, we get e to the x over 2x, derivatives on both sides. Remember, e to the x differentiates to e to the x. Well, this is still not quite solved, right? The numerator is still going to infinity, the denominator is still going to infinity. However, our rule doesn't say we can have to stop there. We just differentiate again. In fact, as long as we still have an indeterminate form, we can just keep applying the rule over and over again. And I should emphasize that you do have to have the indeterminate form. You can't do it if you don't have this indeterminate form. And in fact, that's the case here. Now we have e to the x over 2. This is not an indeterminate form anymore. It's not an infinity over infinity case. It's an infinity over a finite. And so, in fact, infinity over 2 in this case is just going to go to infinity. So that's the limit of e to the x over x squared as x goes to infinity. Kind of a way to think about this is that the e to the x is getting bigger faster than the x squared, which isn't a surprise. This is an exponential, but that means this whole function is going to go to infinity. Now, let's take one more example. Okay, if we just remind ourselves of all our indeterminate forms, only the top couple actually looked like fractions. We had that kind of ratio. Well, what if we have the case where we have a 0 times by an infinity? Okay, and that's exactly what we have here. We're going to take the limit as x approaches 0 from the right of x times by e to the 1 over x. Okay, so this is clearly 0. 1 over 0 is going to infinity, so it's e to the infinity, so it's infinity. So we get a 0 times infinity case. And, well, we don't have this ratio, right? L'Hopital's rule relied on us having a ratio that we could differentiate. So in these cases where we see something multiplied, we're going to sort of artificially create a ratio. Okay, still true. That instead of multiplying by x here, we can divide by 1 over x. Okay, these two things are still equal. Okay, notice we don't have the LHR this time. We've not actually applied the rule yet. All we've done is done a little bit of algebra to get that 1 over x in the denominator. But now we can apply L'Hopital's rule. Okay, we have to use the chain rule in the numerator and just differentiate the denominator. And so we use L'Hopital's rule there. We get minus 1 over x squared e to the 1 over x. That's the chain rule piece. And in the denominator we get minus 1 over x squared. And of course, just obvious here that there's a nice little cancelling out we can do. And so now we get the limit as x approaches 0 of e to the 1 over x. Well, the 1 over x is going to infinity, therefore e to the infinity is going to infinity. Okay, so this is another example of how we can apply L'Hopital's rule, even though we didn't have something that obviously looked like a L'Hopital's case in the first instance. And there are other variations on this, but I think since we're just doing the basics, that will do for now.